This video is going to cover integrals that involve the inverse trig functions. Earlier in this course, we learned how to take the derivatives of our inverse trig functions, arcsine, arctan, arcsecant, etc. We're going to use the patterns of those derivatives to come up with some formulas for some antiderivatives. So I have written on the screen 3 basic antiderivative patterns that will give us inverse trig functions. The first pattern is when you are integrating a constant, like 1, over the square root of a constant. So the a, right there where it says a squared, that is a constant, minus u squared, where the u is the variable, or the x. We will always get arcsine of u over a plus c. I'm not going to derive this antiderivative for you. If you are continuing with Calc 2, you'll learn how you can actually derive this using a trig substitution. The second antiderivative we have is a constant, like 1 du over a squared, which would be a constant, plus u squared. The u squared part is our variable squared. The antiderivative of that is 1 over a, arctan of u over a plus c. And then finally, the last pattern we have is du over u, square root of u squared minus a squared. Again, the u is the variable. I know that because there's a du in the integral. The a is a constant. I'm going to get 1 over a, arcsecant, absolute value of u over a plus c. So one of the things to notice about these patterns is you get the arcsine function when you're integrating a square root. You have a square root in the denominator, constant minus the x squared. Arctan involves constant plus the x squared. There's no square root in that one. And then the arcsecant one has the x squared minus the constant in the square root. There is that extra x outside of the square root as well. So let's see how this works by doing some practice problems. I want to find the following antiderivatives. I'm going to start by trying to integrate 1 divided by 5 plus x squared. An ordinary u substitution wouldn't work here. If I let u equal the denominator, the 5 plus x squared, my du would have a 2x dx, and because there's no x in the numerator, I'm not going to be able to use that u sub. Instead, this fits into our arctangent pattern because we have 1 over constant plus x squared. That fits into the pattern 1 divided by a squared plus u squared du. In this particular problem, the a squared is 5 and the u squared is the x squared. That means a would be square root of 5 and u would equal x. And if u is 1x, then du would be 1 dx. So this integral fits into this pattern 1 over a squared plus u squared du. That means my antiderivative is going to be 1 over a, so 1 over root 5, arctan. I wrote that as inverse tangent. Those are the exact same thing. So we've got inverse tangent of u over a, which in this case would be x over square root of 5, and then plus c. In my second example, we're integrating 1 over 7 plus 4x squared dx. This also fits into that arctan pattern. We have constant plus the x squared in the denominator. To get this problem to fit into that arctan pattern, the a squared is the 7 and the u squared is 4x squared. That means a is root 7 and u is 2x. So my du now is actually 2 dx. Again, because u is not just equal to x, u is 2x. We're technically doing a u sub here. U is 2x, so my du would be 2 dx. I can rewrite this integral as 1 over a squared plus u squared, but then the dx is actually going to turn into a du divided by 2. So I'm going to replace that dx with du divided by 2. And I can take that divide by 2. It's the same thing as a 1/2. I can pull that out front. That's just a constant. So this integral is actually equivalent to 1/2 integral of 1 over a squared plus u squared du, where a is root 7 and u is 2x. So plugging that into my pattern, I'm going to keep the 1/2 the constant. Then we get 1 over a, so 1 over root 7, inverse tangent 2x over root 7. That was my u over a, plus c. I'll just write this as 1 over 2 root 7, inverse tangent 2x over root 7, plus c. My next example, we're going to integrate 1 over the square root of 6 minus 9x squared. This now fits into my arc sine pattern. We have a square root in the denominator, constant minus something with an x squared. That's our arc sine pattern. Once again, I want to point out a traditional u substitution would not work. If you let u equal the 6 minus 9x squared, your du would end up having an x in it. And so you would need an x in the numerator to get that traditional u sub to work. Okay, so to get this to fit into my arc sine pattern, the a squared has to be the 6, and the u squared would be the 9x squared. So a is root 6, u is 3x. That means du is 3 dx. So this is the same as the integral of 1 divided by a squared minus u squared times du divided by 3. Notice I replaced that dx with du divided by 3. That's because du is 3 dx, so we could solve for dx by dividing by 3, and that means dx is du over 3. Pulling the 1/3 out front, now I have something that matches my arc sine pattern perfectly. So using my formula, I am going to get 1/3, my constant, arc sine of 3x over root 6 plus c. That was my u over a, and then of course plus c. Here's my next example. I have antiderivative of 1 over x square root 3x squared minus 4. This one fits into the arc secant pattern. We have the x outside of that square root. We have a 3x squared minus 4, so variable squared minus constant inside the square root. So I'm going to let u squared equal to 3x squared, and a squared equals 4. So I'm trying to get my pattern to fit inside that square root. I need it to be u squared minus a squared. If u squared is 3x squared, then u would be root 3 times x. If a squared is 4, a is 2. So my du would be root 3 times dx. And if I solve for dx by dividing by root 3, dx is du divided by root 3. So plugging that into my integral, let's see, we've got 1 over, we still haven't done anything with that x that's outside of the square root, but we do now have square root u squared minus a squared, and the dx becomes du divided by root 3. I need this integral to be in terms of u only. I need it to fit the pattern I have above. So I need to replace that x that's outside of the square root with something that involves a u. And if u is root 3 times x, I can actually solve that for x. And x would have to be u divided by root 3. So I'm going to replace that x outside of the square root with u divided by root 3. And we can actually simplify this because if I multiply straight across, my numerator is just 1 du, but in the denominator, we have this u divided by root 3, and then times root 3. Those root 3's actually end up canceling out, and I'm left with something that fits into that arc secant pattern perfectly. So my antiderivative is going to be 1 over a, which in this case would be 1 over 2, arc secant root 3x over 2 plus c. Let's take a look at another example that's a little bit different. Now I have antiderivative 1 over x squared minus 6x plus 15. This almost looks like the arctan pattern. We have an x squared, and then we have that plus 15. The problem here is that minus 6x. That middle term is making this not fit into my arctangent pattern. But it turns out we can do a little bit of algebra. We can actually complete the square so that we do end up getting a constant plus something with an x squared. So first, I'm just going to do a really fast review on completing the square in case you've forgotten how to do that. If I have x squared plus 10x, and I want to turn this into a perfect square trinomial, I look at the number in front of the x, I look at the 10, I cut it in half. 10 divided by 2 is 5, and 5 squared is 25. So if I add 25, this is now a perfect square trinomial. And what that means is the x squared plus 10x plus 25 can be factored as x plus 5 squared. That's because 5 plus 5 gives me 10. 5 times 5 gives me 25. X squared minus 8x, if I want to complete the square, I look at the number in front of the x, 8. I divide it by 2. 8 divided by 2 is 4, and then we square it. 4 squared is 16. So if I add 16, this is a perfect square trinomial, and we can factor it as x minus 4 quantity squared. Notice because we have that minus 8x, when we factor it, it becomes an x minus 4. Again, just to check, minus 4 plus minus 4 gives us the minus 8. Minus 4 times minus 4 gives us that plus 16. One more, x squared plus 5x. To complete the square, I take the 5, divide it by 2, and square it. 5 halves squared becomes 25 fourths. So I add 25 fourths. To factor, this becomes x plus 5 halves. The pattern is it's always going to have the sign that you had in front of your linear term. So x, this one's going to be x plus, and then it's whatever you squared. 5 halves is what we squared to get the 25 over 4. So x plus 5 halves quantity squared. All right, so back to our problem. We're going to focus on the denominator. In the denominator, I have x squared minus 6x plus 15. I'm going to focus just on those first two terms only and complete the square. To do that, I look at the number in front of the x, so I look at the 6. 6 divided by 2 is 3. 3 squared is 9. So to complete the square, I'm going to have to add a 9. But I don't actually want to change the problem. I want to find the antiderivative of the function that was given to me. So since I added a 9, I'm going to go ahead and subtract a 9 as well. That means this denominator is going to be unchanged. By adding and subtracting 9, technically we've added 0, so we haven't actually changed the expression. Those first three terms can be factored as x minus 3 squared, and then 15 minus 9 is 6. So this problem becomes antiderivative of 1 over x minus 3 squared plus 6 dx. This now fits into that arctangent pattern. The a squared is the constant, it's the 6, so a is square root of 6. U squared has to be the variable term, so u squared would be x minus 3 squared. That means u is x minus 3, and du is 1 dx. So this integral turns into integral of 1 over u squared plus a squared du. That fits into my arctangent pattern perfectly, so I'm going to get 1 over square root of 6, arctan, x minus 3 over root 6 plus c. That's my 1 over a, arctan u over a, plus c. My next example, cosine x over 9 plus sine squared x is the function we want to integrate. This one actually fits into our arctangent pattern. It's a little bit harder to see just by looking at it. But notice in the denominator, you have a constant, which is 9, plus something with a variable squared. Let's see what happens when we try to put this into that arctan pattern. I would say the a squared is 9, and the u squared is sine squared of x. So a is 3, and u would be sine x. Du, the derivative of sine x is cosine x, so du would be cosine x dx. And so it turns out it's actually a good thing I have a cosine x in the numerator, because that is my du. So this does match that pattern, du over a squared plus u squared. So I'm going to just replace the cosine x dx with du. Since I just figured out du is cosine x dx. And then the denominator is my a squared plus u squared. This fits into that arctangent pattern. So my antiderivative is going to be 1 over a, so 1 over 3, arctan of u over a, which in this case would be sine x over 3, and then plus c. All right, I have one more example. Let's try to integrate 2x minus 5 divided by x squared plus 4x plus 5. So the first thing I would try with this problem is, does a u sub work? We have something with an x squared in the denominator, and I have something with a 2x in the numerator. So trying a u sub is a really good idea in this case. I would let u equal the denominator, x squared plus 4x plus 5. Let's see what happens when we try to do that u sub. My du would be 2x plus 4 dx. So dx is du divided by 2x plus 4. If I try to do the u sub here, because we have a 2x minus 5 in the numerator, and my dx was du over 2x plus 4, those factors don't actually cancel out. I can't get this integral in terms of u only. So it's looking like this u sub is not going to work. The u sub would work if my numerator had a 2x plus 4 or a multiple of 2x plus 4. But again, the problem is that minus 5. We have 2x minus 5 instead. I really want those terms to cancel so that I can use my u sub. So again, that numerator has to be a 2x plus 4, because then the u sub would work. So I'm going to do a little bit of a trick here. My numerator was 2x minus 5. I'm going to add 4 and then subtract 4. This reminds me of that completing the square process, where we're technically adding 0 because we're adding and subtracting the same number. And this is going to allow me to separate this function into two separate functions that can be integrated. So I'm going to think of this as 2x plus 4, so 2x plus 4, and then minus 9, all over x squared plus 4x plus 5. I can then break this up into two separate fractions and consider the fraction 2x plus 4 over x squared plus 4x plus 5 plus minus 9 over x squared plus 4x plus 5. And the idea is that 2x plus 4 over x squared plus 4x plus 5, that's something where the u sub can work. And the second integral, the one with the constant on top, that's going to fit into my arctan pattern. So I'm going to do both of these integrals separately. Starting with the integral on the left, I'm going to use my u sub. I actually already started that earlier, so I'm just going to jot down what I had written down earlier. U was the denominator, the x squared plus 4x plus 5. So du is 2x plus 4 dx. So that means we can rewrite this integral as 1 over u du. Those 2x plus 4's cancel out, so 1 over u du. That's something I can integrate. The antiderivative of 1 over u is natural log absolute value of u plus c, or natural log absolute value x squared plus 4x plus 5 plus c. Now the integral on the right, because we don't have an x in the numerator, we have a minus 9 or a constant in the numerator. I'm going to see if I can get this to fit into my arctan pattern. This reminds me of the previous example where I do have an x squared and a constant in the denominator, but we also have this middle, this 4x term. So we're going to use the method of completing the square to try to manipulate this denominator so it fits into that arctan pattern. So to complete the square, I just look at the first two terms, x squared plus 4x. Half of 4 is 2. 2 squared is 4. So I'm going to add 4, and I'm going to subtract 4 as well. The first three terms can be factored as x plus 2 quantity squared, and then 5 minus 4 gives me 1. So we have the integral negative 9 divided by x plus 2 squared plus 1 dx. We are going to let the u squared equal x plus 2 squared. So u is x plus 2. A squared is 1, so a is 1. Du would be 1 dx. So this integral is negative 9 over u squared plus a squared du. We can pull that negative 9 out front, and now this fits into that arctan pattern perfectly. We're going to get that constant, that negative 9, times 1 over a, so 1 over 1, arctan u over a, so that's going to be arctan x plus 2 over 1 plus c. And then my final answer is going to be the sum of these two antiderivatives. So final answer, natural log, absolute value, x squared plus 4x plus 5, minus 9 arctan of x plus 2 plus c. All right, that was my last example. I know there's a lot of algebra going on in these problems, so please reach out if anything in this video is unclear.